Have you ever looked up at the night sky and wondered how far we could actually go? Not just to the moon or Mars, but really out there, to the edge of the solar system, to other stars, to distant galaxies? How far can humans actually travel through space before the universe itself says no? Before the laws of physics draw a line we cannot cross? Let's start close to home, with destinations we've already reached, or could reach in your lifetime. The Moon sits about 384,000 kilometers from Earth. We've been there. 12 humans walked on its surface between 1969 and 1972. The Apollo missions proved something fundamental. Space travel is possible. Humans can leave Earth, can survive in the void, can return home safely. The technology was primitive by today's standards. The computers on board Apollo 11 had less processing power than your smartphone, and yet they made it. This tells us something important about human capability, about determination, about what's possible when we decide something matters. But the Moon is just the beginning. The next logical destination is Mars. The red planet orbits the Sun at an average distance of about 228 million kilometers from Earth. That distance changes as both planets move in their elliptical orbits. At closest approach, Mars is about 55 million kilometers away. At its farthest, over 400 million. Current spacecraft take between 6 and 9 months to make the journey. NASA's Perseverance rover launched in July 2020 and landed in February 2021. 7 months of travel for a robot the size of a car. For humans, the challenge is more complex. You need life support, radiation shielding, food, water, air, exercise equipment to prevent muscle and bone loss in zero gravity, psychological support for the crew, and enough fuel to slow down when you arrive. Then you need to survive on Mars itself, a planet with almost no atmosphere. Surface temperatures averaging -63 degrees Celsius. Dust storms that can engulf the entire planet. No liquid water on the surface. No breathable air. No protection from cosmic radiation. Despite all this, Mars is achievable. SpaceX is developing the Starship system specifically for Mars missions. NASA has plans for crewed missions in the 2030s. China and other nations have similar ambitions. Within your lifetime, humans will almost certainly walk on Mars. We will establish bases, conduct research, perhaps even begin the long process of terraforming, making Mars more Earth-like, more habitable. This is not fantasy, this is engineering, hard, expensive, dangerous engineering, but possible, absolutely possible. If this content is sparking your curiosity, if you're enjoying this journey through the cosmos, please hit that subscribe button and give this video a thumbs up. It really helps this channel grow and allows me to create more content like this. Your support truly matters. Beyond Mars, things get harder. The asteroid belt sits between Mars and Jupiter, roughly 200 to 300 million kilometers from the Sun. Thousands of rocky bodies orbit there, some as small as pebbles, others hundreds of kilometers across. Dawn, a NASA spacecraft, visited the two largest asteroids, Vesta and Ceres, between 2011 and 2018. The mission took years and required innovative ion propulsion technology. For humans, asteroid missions are possible, but they're longer and riskier than Mars. The rewards might be worth it though. Asteroids contain metals, water ice, resources that could support deeper space exploration. Jupiter is the first of the gas giants. It orbits about 778 million kilometers from the Sun. At its closest to Earth, it's around 628 million kilometers away. The Juno spacecraft, currently orbiting Jupiter, took 5 years to get there after launching in 2011. For humans, this distance represents a serious barrier. The journey would take years with current propulsion technology. Radiation near Jupiter is intense. The planet's magnetic field traps charged particles, creating radiation belts far more dangerous than Earth's Van Allen belts. A human crew would need heavy shielding, advanced life support, psychological preparation for years in a small spacecraft with the same few people. But let's say we solve those problems. Let's say we develop faster propulsion, nuclear engines perhaps, or fusion drives. We could reach Jupiter in months instead of years. We could explore its moons. Europa, with its subsurface ocean potentially harboring life. Ganymede, the largest moon in the solar system. Io, with its volcanic surface. Callisto, ancient and cratered. These worlds are, scientifically, priceless. They could teach us about the formation of the solar system, about the possibility of life beyond Earth, about resources we might use for further exploration. Saturn sits even farther out, about 1.4 billion kilometers from the Sun. The Cassini spacecraft spent 13 years exploring Saturn and its moons after a 7-year journey to get there. It discovered geysers of water erupting from Enceladus, lakes of liquid methane on Titan, complex dynamics in Saturn's rings. For humans, Saturn represents the practical edge of crewed exploration with anything resembling current technology. The distances are enormous, the travel times measured in years, the risks compounding with every additional day away from Earth. Uranus and Neptune are the ice giants. Uranus orbits about 2.9 billion kilometers from the Sun. Neptune is about 4.5 billion kilometers out. Voyager 2 is the only spacecraft to have visited them, flying past in 1986 and 1989 respectively. Voyager 2 launched in 1977. It took 9 years to reach Uranus and 12 to reach Neptune. These are one-way missions for robots built to last decades in the harsh environment of space. For humans, these distances push the boundaries of what's feasible. Even with advanced propulsion, you're looking at many years of travel each way. And then there's Pluto, the dwarf planet that captured our hearts and imaginations. Pluto orbits in the Kuiper Belt, a region of icy bodies beyond Neptune. Its distance from the Sun averages about 5.9 billion kilometers, though its elliptical orbit brings it as close as 4.4 billion and as far as 7.4 billion. New Horizons, the spacecraft that gave us our first close-up views of Pluto, took 9.5 years to get there after launching in 2006. It traveled faster than any previous spacecraft and still took nearly a decade. Think about that for a moment. 9.5 years. That's longer than most people stay in one job, longer than many marriages last, longer than the entire childhood of a person born the year it launched. And New Horizons didn't stop at Pluto. It couldn't. It was moving too fast. It flew past cameras and instruments, gathering data for a few precious hours, then continued into the dark. In 2019, it visited Arakoth, formerly known as Ultima Thule, an ancient icy object another billion kilometers beyond Pluto, the most distant world ever explored by humanity. For a human crew, reaching Pluto would require something beyond our current capabilities. Not just faster engines, but closed-loop life support systems that can recycle air and water perfectly for decades. Artificial gravity to prevent the devastating effects of long-term weightlessness. Hibernation technology, perhaps, to reduce the psychological burden of years in transit. Food production in space. Medical facilities capable of handling emergencies light hours from Earth. By the time a radio signal reaches Earth from Pluto, roughly 5.5 hours have passed. If something goes wrong, you're on your own. Yet even Pluto isn't the edge of the solar system, not really. Beyond the Kuiper Belt lies the scattered disk, where objects have been flung into distant, eccentric orbits by gravitational interactions with Neptune. Beyond that, the Oort cloud, a vast spherical shell of icy bodies surrounding the solar system. The Oort cloud is thought to extend from about 2,000 astronomical units to maybe 100,000 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, roughly 150 million kilometers. So we're talking about distances measured in trillions of kilometers. The Oort cloud has never been directly observed. We infer its existence from the long-period comets that occasionally dive into the inner solar system. These comets come from random directions, suggesting a spherical distribution of source material. Voyager 1, humanity's most distant spacecraft, crossed into interstellar space in 2012 at a distance of about 121 astronomical units. It's still technically within the Sun's sphere of influence, but beyond the heliopause where the solar wind gives way to the interstellar medium. Voyager 1 has been traveling for over 45 years and won't reach the inner edge of the Oort cloud for another 300 years. It won't exit the Oort cloud for 30,000 years. Let that sink in. 30,000 years. That's longer than recorded human history, longer than agriculture, longer than civilization itself. And that's just to cross through a region of our own solar system. This is where the distances start to become not just challenging, but genuinely incomprehensible, where the numbers stop meaning anything intuitive, where even exponential notation feels inadequate. So let's talk about the next frontier, the stars. Our nearest stellar neighbor is Proxima Centauri, part of the Alpha Centauri system. It's about 4.24 light-years away. A light-year is the distance light travels in 1 year, moving at roughly 299,792 kilometers per second. That works out to about 9.5 trillion kilometers per year. Proxima Centauri is therefore about 40 trillion kilometers away. Voyager 1, our fastest deep space probe, would take over 73,000 years to reach Proxima Centauri if it were headed that direction, which it isn't. This is the wall. The barrier that makes interstellar travel seem impossible. 73,000 years is not a journey, it's a geological epoch. It's enough time for entire species to evolve, for civilizations to rise and fall, for languages to emerge and disappear. No human crew could survive it. No spacecraft we can currently build would remain functional. The cosmic radiation alone would degrade electronics and materials. Micrometeorite impacts would slowly erode the hull. Systems would fail. Entropy would win, but we're clever, we're innovative, we think big. So scientists and engineers have proposed ways around this problem. The first approach is simple: go faster, much faster. If we could reach 10% of light speed, the journey to Proxima Centauri would take about 42 years. Still a lifetime, but potentially manageable. A crew could depart young and arrive middle-aged, or we could use generation ships. Spacecraft large enough to support entire communities for multiple generations. The original crew would have children, those children would have children, and their children might arrive at the destination. How do we reach 10% of light speed? Chemical rockets won't do it. They're too inefficient. Nuclear propulsion is better. Project Orion, conceived in the 1950s, proposed using nuclear explosions for propulsion. Detonate bombs behind the spacecraft and ride the shockwave. Crude, but potentially effective. The design studies suggested speeds up to 5% of light speed might be achievable. The project was abandoned, partly due to the Partial Test Ban Treaty of 1963, which prohibited nuclear weapons tests in space. Nuclear fusion offers another path. Fusing hydrogen into helium releases tremendous energy. This is what powers the Sun. If we could harness fusion for propulsion, we might reach significant fractions of light speed. Several designs exist on paper. The Daedalus project, studied by the British Interplanetary Society in the 1970s, proposed a fusion rocket that could reach 12% of light speed. It would take about 40 years to reach Barnard's star, 6 light-years away. The spacecraft would be enormous, require decades to build, cost more than any single project humanity has ever undertaken. But the physics checks out. It's possible in principle. Then there's antimatter. When matter and antimatter meet, they annihilate completely, converting all their mass into energy according to Einstein's famous equation E equals mc squared. This is the most efficient energy source theoretically possible. A tiny amount of antimatter contains staggering energy. If we could produce and store antimatter safely and use it for propulsion, we might reach speeds approaching a significant fraction of light speed, perhaps 20 or 30%. The problem is production. Making antimatter requires enormous energy input. Currently, we can only produce tiny amounts at facilities like CERN, and storing it is extraordinarily difficult. Antimatter annihilates instantly upon contact with normal matter. You need magnetic or electric fields to keep it suspended. Technology we're only beginning to develop. Another fascinating proposal is the solar sail. Instead of carrying fuel, you use photons from the sun or from lasers to push your spacecraft. Light carries momentum. When photons reflect off a surface, they transfer that momentum. A large, ultra-thin reflective sail could be accelerated by sunlight or by powerful lasers beamed from Earth or from satellites. The Planetary Society's Light Sail 2, launched in 2019, demonstrated that solar sailing works. It successfully changed its orbit using sunlight alone. For interstellar missions, the Breakthrough Starshot initiative proposes using ground-based lasers to accelerate tiny spacecraft equipped with light sails to 20% of light speed. These wouldn't be crewed missions. The spacecraft would be about the size of a microchip, weighing just grams. But they could reach Proxima Centauri in about 20 years and send back data. Breakthrough Starshot represents a radical rethinking of space exploration. Instead of sending massive crewed vessels, send thousands of tiny probes. Most might fail, but some would succeed. They'd carry cameras, sensors, and communication equipment. They'd fly past the Alpha Centauri system at incredible speed, gathering data for hours or days, then transmit it back to Earth. The transmission would take over 4 years to arrive, traveling at light speed, but we'd have images, data, proof that we can reach other star systems. It would be the first step toward true interstellar exploration. Of course, these tiny probes can't carry humans. For crewed missions, we need different solutions. One idea is the generation ship, a spacecraft large enough to be self-sustaining, with agriculture, industry, closed-loop ecosystems, a population of thousands living, working, having children, growing old and dying while the ship travels between stars. Their descendants would arrive at the destination centuries later. This concept appears frequently in science fiction, but the engineering challenges are staggering. You'd need to create a miniature world, a biosphere that remains stable for hundreds of years, social systems that prevent conflict and maintain purpose across generations, genetic diversity sufficient to avoid inbreeding, technology that can be maintained and repaired without external resources. Some researchers have studied the minimum viable population for generation ships. Estimates range from a few hundred to several thousand, depending on assumptions about genetic management and social structure. There's also the psychological question. How do you motivate people to live their entire lives for a destination they'll never see? How do you prevent social collapse or mutiny? These aren't just engineering problems, they're problems of sociology, psychology, and philosophy. Another approach is hibernation, or suspended animation. If we could safely put people into a state of reduced metabolism for years or decades, the psychological burden of long journeys would disappear. You'd go to sleep near Earth and wake up near another star. This technology doesn't exist yet, but research is ongoing. Some animals naturally hibernate for months, bears, squirrels, Certain frogs can even freeze solid and revive. Understanding the mechanisms could lead to induced hibernation for humans. Medical advances in preserving organs for transplant point toward longer-term suspension. It's not impossible, just very difficult, and untested at the timescales we'd need. Then there are more exotic proposals, wormholes, shortcuts through space-time connecting distant points. Einstein's equations allow for them mathematically, but creating or stabilizing a wormhole would require exotic matter with negative energy density. We've never observed such matter, it might not exist. Even if it does, manipulating it would require technology far beyond anything we possess. Wormholes remain firmly in the realm of speculation. Fascinating to think about, fun to explore in theory, but not something we can count on. Warp drives are another staple of science fiction. The idea is to contract space in front of your ship and expand it behind, creating a bubble that moves faster than light, while the ship inside remains stationary relative to its local spacetime. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, provides a mathematical framework for this. But again, it requires exotic matter and enormous amounts of energy. Some estimates suggest you'd need the mass energy equivalent of Jupiter or more. Recent refinements have reduced the energy requirement somewhat, but they're still astronomical, and we still don't know if exotic matter exists or how to produce it. These concepts show us something important. The laws of physics don't absolutely forbid faster-than-light travel, they just make it extraordinarily difficult, perhaps impossible with any technology we can imagine. But the universe is under no obligation to make things easy for us. It simply is what it is. And we have to work within its rules. Let's talk about where we could go if we had the technology. What destinations would be worth the journey? Proxima Centauri is the closest star, but it's a red dwarf, smaller and cooler than our Sun. It does have at least 2 planets. Proxima Centauri, B, orbits in the habitable zone where liquid water could exist. It's slightly larger than Earth, but Proxima Centauri is a flare star. It releases powerful bursts of radiation that could strip away a planet's atmosphere or sterilize its surface. Whether life could exist there remains an open question. Alpha Centauri, A and B, the other 2 stars in the system, are more Sun-like. Alpha Centauri A is slightly larger and brighter than our Sun. Alpha Centauri B is slightly smaller. They orbit each other in a binary dance. Whether they have planets in stable orbits within their habitable zones is still being investigated, but they're promising targets. If we're going to send humans to another star system, Alpha Centauri makes sense simply because it's closest. Barnard's star, about 6 light-years away, is another nearby target. It's also a red dwarf and has at least 1 planet. Tau Ceti, about 12 light-years distant, is a Sun-like star with multiple planets. Some might be in the habitable zone. These nearby stars represent our immediate stellar neighborhood. Within about 15 light-years of Earth, there are several dozen star systems. Many likely have planets. Some of those planets might be habitable. The Kepler Space Telescope and its successor TESS have revolutionized our understanding of exoplanets, planets orbiting other stars. We now know that planets are common. Most stars have them. Rocky planets in habitable zones are not rare. Within our galaxy alone, there could be billions of Earth-like worlds. The Milky Way contains between 100 billion and 400 billion stars. Even if only a small fraction have habitable planets, the numbers are staggering. The galaxy is full of destinations, but here's the challenge. The Milky Way is vast, incomprehensibly vast. Our galaxy is roughly 100,000 light-years across. Light, traveling at the fastest speed possible, takes 100,000 years to cross from one side to the other. The Sun sits about 26,000 light-years from the galactic center. We orbit the galaxy once every 225 to 250 million years. A galactic year. The last time Earth was in this position, dinosaurs hadn't even appeared yet. Even if we could travel at light speed, which we can't, reaching the far side of the galaxy would take 100,000 years. And remember, nothing with mass can actually reach light speed. The closer you get, the more energy you need. It's an asymptotic limit, approachable but never reachable. Realistically, even with advanced propulsion, we might achieve 10 or 20% of light speed, maybe 30 if we're very clever and very determined. That means crossing the galaxy would take somewhere between 300,000 and 1 million years. No human civilization lasts that long. No government, no company, no institution has ever persisted for even 10,000 years. The oldest continuous civilizations on Earth are measured in thousands of years, not hundreds of thousands. The very concept of a million-year project defies everything we know about human organization and motivation. And yet, if we want to explore the galaxy, these are the timescales involved, unless we think differently. What if exploration isn't done by individuals or even by generations, but by waves of expansion? Imagine we establish a colony on a planet around Proxima Centauri. That takes perhaps a century with advanced but plausible technology. That colony grows, builds its own infrastructure, eventually launches its own missions to nearby stars. Each colony becomes a stepping stone, a hub for further exploration. Over thousands of years, humanity spreads outward in an expanding sphere, not as a coordinated effort from Earth, but as a cascade of independent migrations. This is sometimes called the percolation model of galactic colonization. You don't need any single journey to span the galaxy. You need many short journeys, each building on the last. Computer simulations suggest that even with slow ships and long pauses between waves, a species could spread across the entire galaxy in a few million years. That sounds like a long time. And it is. But it's a blink of an eye in cosmic terms. The Milky Way is about 13 billion years old. A few million years is less than 1% of its age. This raises a famous question. The Fermi paradox. Named after physicist Enrico Fermi, who supposedly asked during a lunch conversation in 1950, "Where is everybody?" If intelligent life is common in the galaxy, and if technological civilizations tend to explore and colonize, then why haven't we seen any evidence of them? The galaxy is old enough for life to have emerged billions of years before Earth. If even one species had decided to expand across the stars, they should be everywhere by now, including here. So where are they? Hundreds of proposed solutions exist. Maybe intelligent life is extraordinarily rare. Maybe technological civilizations destroy themselves before spreading beyond their home systems. Maybe interstellar travel is harder than we think. Maybe advanced civilizations lose interest in exploration. Maybe they're here but hiding. Maybe they exist in forms we don't recognize. Maybe the galaxy is full of ruins, dead civilizations that rose and fell long before we evolved. Each explanation has implications. None are comforting. The Great Filter hypothesis suggests there's some barrier that prevents life from spreading across the galaxy. Either it's behind us, something incredibly unlikely that we've already passed, or it's ahead of us, some danger that destroys civilizations before they mature. If it's behind us, we're lucky, rare, precious. If it's ahead of us, we're in danger. The silence of the cosmos might be a warning, but let's stay optimistic. Let's assume we can spread to the stars. What are the limits? We've talked about the Milky Way. What about beyond? The nearest major galaxy is Andromeda, about 2.5 million light-years away. Even traveling at light speed, which again is impossible for anything with mass, The journey would take 2.5 million years, at realistic speeds, tens or hundreds of millions of years, and that's just to our nearest large neighbor. The local group, the cluster of galaxies containing the Milky Way and Andromeda, spans about 10 million light-years. Beyond that, the Virgo supercluster, which contains the local group and many other galaxy clusters, extends about 110 million light-years. And beyond that, the observable universe stretches about 93 billion light-years across. This number might seem strange. If the universe is only about 13.8 billion years old, shouldn't the observable universe be only about 27.6 billion light-years across? Light traveling in both directions for 13.8 billion years? The answer involves cosmic expansion. The universe isn't just big, it's growing. Space itself is expanding. Galaxies are moving away from each other, not because they're traveling through space, but because the space between them is increasing. The farther away a galaxy is, the faster it appears to recede. This is Hubble's law, discovered by Edwin Hubble in the 1920s. The expansion stretches the wavelength of light traveling through it, shifting it toward the red end of the spectrum. This is cosmological redshift. Because of expansion, objects that emitted light 13.8 billion years ago are now much farther away than 13.8 billion light-years. The most distant objects we can observe are now about 46.5 billion light-years away in any direction. That gives the observable universe its diameter of about 93 billion light-years. But here's the critical point. The universe is expanding faster than we can travel through it, and the expansion is accelerating. Dark energy, the mysterious force driving this acceleration, makes up about 68% of the universe's total energy density. We don't know what it is. We just know it's pushing space-time apart. At large scales over billions of light-years, the expansion velocity exceeds the speed of light. This doesn't violate relativity. Space itself can expand faster than light. It's not moving through space. It's the space that's moving. This creates a cosmic horizon, a boundary beyond which we can never reach, no matter how fast we travel or how long we try. Galaxies beyond this horizon are receding faster than light. The light they emit will never reach us. The space between us and them is growing faster than light can cross it. This horizon is currently at about 16.5 billion light-years. Everything beyond that is forever inaccessible, unreachable, lost to us. And it gets worse. Because the expansion is accelerating, the cosmic horizon is actually shrinking in terms of what we can reach in the future. Galaxies that are currently within reach will eventually cross the horizon and become unreachable. In the far future, billions of years from now, the Milky Way and Andromeda will have merged. Our local group of galaxies will be gravitationally bound together. But everything else will have receded beyond the horizon. Future observers in that distant epoch will look out and see only their local cluster. The rest of the universe will have disappeared, faded into darkness. Redshifted into invisibility, this means there's a window, a finite period during which intergalactic travel is even theoretically possible. We're living in that window. In billions of years it will close. The universe will still exist, but it will be fundamentally inaccessible. Each galaxy cluster will be an island, isolated, alone, forever. So let's quantify the limits. Within our galaxy, we could potentially explore and colonize millions of star systems given enough time and technology. This is a project for thousands or millions of years, but it's not forbidden by physics. Within our local group, we could reach dozens of galaxies, the Milky Way, Andromeda, Triangulum, and various dwarf galaxies. This extends our potential range to a few million light-years, a timescale of tens or hundreds of millions of years. Still long, but not impossible in principle. Beyond the local group, things become truly challenging. The expansion of space works against us. The farther we try to go, the more we're fighting cosmic expansion. The Virgo supercluster might represent an absolute practical limit. Beyond that, the distances and timescales become so extreme that it's hard to imagine any civilization maintaining continuity or purpose. We're talking billions of light years, billions of years of travel. Empires could rise and fall. Species could evolve into something unrecognizable. The very meaning of humanity might change beyond recognition. And then there's the cosmic horizon, the ultimate boundary. Beyond about 16.5 billion light-years, travel becomes impossible. Not difficult, not impractical, impossible. The laws of physics forbid it. Space expands too fast. You'd need to exceed light speed just to maintain your distance, let alone get closer. And you can't, nothing can. This is the edge of the accessible universe, the absolute limit of where humans, or anything we might become, can ever go. Let's put this in perspective. The observable universe contains about 2 trillion galaxies. Each galaxy contains billions or trillions of stars. Each star might have planets. The total number of planets in the observable universe is almost incomprehensible, perhaps 10 to the 24th power, a 1 followed by 24 zeros, and yet the vast majority of them are forever beyond our reach, separated from us not by distance alone, but by the expansion of space itself. We live in a universe of almost infinite possibilities, but only a tiny fraction are accessible. And that fraction grows smaller with every passing moment. This is both humbling and tragic. Humbling because it reminds us of our cosmic insignificance. We're one species on one planet orbiting one star in one galaxy among trillions. Tragic because there are worlds out there, perhaps worlds with life, with intelligence, with civilizations asking the same questions we ask, and we'll never know. We'll never meet. We're causally disconnected, forever alone in our corner of the cosmos. But let's not end on despair, because even though the universe is vast and most of it is inaccessible, the part that is accessible is still extraordinary. Our galaxy alone contains hundreds of billions of stars. If even a tiny fraction have habitable planets, we're talking about millions of potential homes for humanity. Millions of worlds to explore, to settle, to transform, to fill with life and intelligence and meaning. And we're just getting started. We've been in space for only about 60 years. We've had the ability to even ask these questions for less than a century. We're infants in cosmic terms, taking our first stumbling steps, looking up with wonder and asking, how far can we go? The answer depends not just on physics, but on us, on our choices, our priorities, our vision for the future. Right now, humanity spends far more on military budgets than on space exploration. The entire budget of NASA for 2024 was about $25 billion. The global military spending for the same year exceeded $2 trillion. Imagine if we redirected even a fraction of that toward space, toward propulsion research, toward building infrastructure, toward taking those first steps to Mars and beyond. The technological capabilities would transform, the timelines would shrink. What seems impossible might become merely difficult. What seems distant might come within reach. There's also the question of artificial intelligence and robotic exploration. We tend to think of space exploration in human terms, brave astronauts venturing into the unknown, but perhaps the future of exploration belongs to machines, AI systems that don't need air or food or water, that can survive radiation, that can be patient for decades or centuries, that can repair themselves, reproduce themselves, evolve themselves. We might send out waves of self-replicating probes. Von Neumann machines, named after mathematician John von Neumann, who studied self-replicating systems. These probes would travel to nearby star systems, gather resources, build copies of themselves, send those copies to more stars, exponential expansion. Within a few million years, such probes could explore the entire galaxy. They'd report back, send data, images, discoveries. We wouldn't need to send humans everywhere. We'd send our ambassadors, our eyes, our representatives, and we'd receive the knowledge, the understanding, the connection to the broader cosmos. Some people find this vision cold, unsatisfying. They want human presence, human experience, human consciousness touching alien worlds, and that's valid. There's something irreplaceable about being there, about standing on another world and looking up at unfamiliar stars, about breathing air that has never been breathed before, about being the first, the pioneer, the explorer. But we might have both. Humans exploring the nearby stars, the local neighborhood, building colonies, creating new branches of human civilization. And machines ranging farther, faster, going where biology cannot. This hybrid approach might be the most practical, the most achievable, the most comprehensive. There's also the possibility that we change ourselves. Human biology evolved for life on Earth. Gravity of 1G, oxygen-rich atmosphere, radiation shielded by a magnetic field and ozone layer. Our bodies are adapted to these specific conditions. In space, we suffer. Bones lose density, muscles atrophy, vision degrades, the cardiovascular system weakens, cosmic radiation damages DNA, long-duration spaceflight takes a toll. Astronauts who spend months on the International Space Station return changed, weakened. They need time to readapt to Earth's gravity. For trips lasting years or decades, these problems compound. Even with exercise and medication, the effects accumulate. Some might be irreversible. This is one reason why Mars colonization is so challenging. Not just getting there, but surviving there long-term, living in reduced gravity, under constant radiation exposure, in a hostile environment that wants to kill you. Human biology wasn't designed for this. But what if we redesign it? Genetic engineering, cybernetic enhancement, adaptation. We're already beginning to understand how to edit genes. CRISPR and other technologies allow precise modifications. We could potentially enhance radiation resistance, improve bone and muscle maintenance in low gravity, increase lifespan, reduce the need for sleep or food, create humans better suited for space, for other worlds, for the long journey between stars. This raises profound ethical questions. Who decides what modifications are acceptable? Who gets access? How do we prevent creating new forms of inequality or discrimination? What does it mean to be human if we start changing our fundamental biology? These aren't just technical questions, they're questions of values, of identity, of what we want to become as a species. Some futurists envision post-human or transhuman futures, where we merge with technology, upload our consciousness into machines, transcend biological limitations entirely. If consciousness can exist in a digital substrate, then space travel becomes radically easier. You don't need life support, just power and shielding for the computer. You could slow down your subjective experience during long journeys. A 100-year voyage might feel like a few hours, or you could speed it up, experience millennia of thought and creativity while traveling between stars. This is speculative. We don't know if consciousness can be uploaded. We don't fully understand what consciousness is, how it emerges from neurons and synapses, whether it's substrate independent, whether a digital copy would really be you or just a simulation that thinks it's you. These are deep philosophical puzzles, but the fact that we can ask them, that we can imagine such futures, that we can begin to work toward them, that's remarkable. Let's return to the practical, to missions that might happen in your lifetime or shortly after. NASA's Artemis program aims to return humans to the Moon and establish a permanent presence there. Not just flags and footprints this time, but bases, infrastructure, resource extraction. The Moon could become a staging ground for deeper space missions. Lower gravity makes launches easier. The far side is ideal for radio telescopes, shielded from Earth's electromagnetic noise. We could conduct astronomy from there unlike anything possible from Earth. Mars remains the primary goal for human exploration this century. Multiple nations and private companies are working toward it. The challenges are immense, but so is the motivation. Mars represents the next giant leap, the first world where humans might become a multi-planet species, where we establish a backup, a second home, insurance against catastrophe on Earth. Whether asteroid impact or nuclear war or climate disaster or pandemic, having humans on multiple worlds increases the chances that humanity survives long-term. Beyond Mars, the moons of Jupiter and Saturn are scientifically compelling but practically distant. Europa and Enceladus both have subsurface oceans, potentially habitable environments. Titan has liquid methane lakes and a thick atmosphere. These are destinations for robotic exploration in the near term. Perhaps human exploration in the late 21st or 22nd century if we develop significantly better propulsion and life support. The asteroid belt and Kuiper belt offer resources, water ice for life support, metals for construction, volatiles for fuel. Mining asteroids could support space-based industry. Manufacturing in zero-gravity or microgravity enables things impossible on Earth: perfect crystals, unique alloys, massive structures that would collapse under their own weight on a planet, space stations, habitats, ships, built in space from space resources without ever touching a planetary surface. This vision of space industrialization has been proposed for decades. Gerard O'Neill, a physicist, designed enormous rotating space habitats in the 1970s, cylinders kilometers long and across, rotating to create artificial gravity, housing thousands or millions of people with sunlight, agriculture, parks, cities in space. These habitats could orbit Earth, or the Moon, or Mars, or be positioned at Lagrange points where gravitational forces balance. They could be moved, repositioned, sent on journeys lasting centuries. O'Neill calculated that building such habitats was technically feasible with 1970s technology. What was missing wasn't knowledge but will and economics. The cost would be astronomical, but costs decrease as infrastructure develops. As mining and manufacturing move into space, as more people and resources are already there, each step enables the next. Bootstrapping, building momentum. There's a concept called the Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964. It classifies civilizations by their energy use. Type 1 controls all the energy available on their planet. Type 2 controls all the energy of their star. Type 3 controls all the energy of their galaxy. Earth isn't even Type 1 yet. We're about 0.73 on this scale, but we're growing. Energy use increases, technology improves, capabilities expand. A Type 2 civilization might build a Dyson sphere, a megastructure surrounding a star to capture all its energy output. This sounds like science fiction, but it's consistent with known physics. You wouldn't build a solid shell. The gravitational stresses would tear it apart. But you could build a swarm. Millions or billions of satellites, solar collectors, habitats, industry, all orbiting the star in a dense cloud, together capturing most of the light, using that energy for computation, manufacturing, survival, growth. Such a structure would be visible from interstellar distances. It would alter the star's spectrum, make it look strange, dimmer in visible light, brighter in infrared as the collected energy is re-radiated as waste heat. Astronomers have searched for such signatures. So far, we've found nothing conclusive. A few candidates. Tabby's star, also known as KIC 8, 4628552 showed unusual dimming patterns. Some speculated it might be an alien megastructure. Further observations suggested natural causes, dust, comets, not aliens. But we keep looking. The absence of detected Dyson spheres ties back to the Fermi paradox. If advanced civilizations exist and build such structures, we should see them. The fact that we don't suggests either they don't exist, they don't build such things, or we're looking in the wrong way. Each possibility tells us something about the universe and our place in it, about what's possible and what might await us. Let's consider time, not just the time it takes to travel, but the time available. The universe is 13.8 billion years old. The Sun is about 4.6 billion years old. Earth is roughly the same age. Life appeared on Earth about 3.8 billion years ago. Complex multicellular life emerged only about 600 million years ago. Humans have existed for maybe 300,000 years. Industrial civilization for about 250 years. Space travel for 60. We're incredibly young, both as a species and as a technological civilization. And yet the universe won't last forever, at least not in a form that supports life. Stars burn through their fuel. The Sun will become a red giant in about 5 billion years. It will expand, engulf Mercury and Venus, possibly Earth. Even if Earth survives, it will be sterilized, all water boiled away, the atmosphere stripped, life impossible. But 5 billion years is a long time, long enough for evolution to produce entirely new forms of life, long enough for humanity to become something unrecognizable, to spread across the galaxy, to reach other galaxies, to build a civilization spanning billions of stars, if we don't destroy ourselves first. Beyond the Sun's death, the universe faces larger-scale endings. Star formation will peak and then decline as gas clouds are exhausted. In about 100 trillion years, the last stars will burn out. The universe will enter the degenerate era. Only brown dwarfs, white dwarfs, neutron stars, black holes, and the cold husks of dead planets. No new stars, no new sources of light. The cosmos will be dark, cold, empty. But even that's not the end. Black holes evaporate through Hawking radiation. Slowly, incredibly slowly. A black hole with the mass of the Sun would take 10 to the 67th power years to evaporate. A 1 followed by 67 zeros. Numbers so large they lose meaning. In the black hole era, lasting from 10 to the 40 up to 10 to the 100 power years, these remnants will dominate. Eventually, they too will vanish. What's left is the dark era. Only photons. Leptons, the most stable subatomic particles. Space continues expanding. The temperature approaches absolute zero. Entropy maximizes. This is heat death, the final equilibrium. No energy gradients, no structure, no complexity, no life, just thin, cold, uniform nothingness, forever. This is the ultimate fate of the universe according to our current understanding. Unless something changes, unless dark energy behaves differently than we think, unless there are new physics we haven't discovered. Unless the universe is cyclical, born, expanding, dying, then reborn. We don't know. The far future is uncertain, but the broad strokes seem clear. The universe is temporary, finite in its useful lifetime. The clock is ticking. This makes our window of opportunity precious. We exist during a brief cosmic moment when stars shine, when planets orbit, when life is possible, when intelligence can emerge and ask questions and build and explore. In the grand timeline of the universe, this moment is fleeting, a spark in the darkness, and we happen to be here, conscious, aware, capable of understanding our place in space and time. So how far can we go? Physically, we're limited by the speed of light and the expansion of space. We can reach perhaps tens of thousands of star systems in our galaxy with realistic technology. Millions if we're patient and committed. We can potentially reach other galaxies in our local group. Andromeda, Triangulum, the dwarf galaxies orbiting the Milky Way. Beyond that, the obstacles become truly formidable. And beyond the cosmic horizon, travel is impossible. The universe itself says no. But there's another dimension to this question. How far can we go in understanding, in imagination, in vision? We've gone from not knowing other galaxies existed to measuring the structure of the entire observable universe. From thinking Earth was the center of everything to understanding we're on a small planet orbiting an average star in an ordinary galaxy among trillions. From believing the heavens were eternal and unchanging to recognizing the universe has a history, a birth, an evolution, an eventual end. We've detected gravitational waves, ripples in space-time predicted by Einstein a century ago. We've imaged black holes, photographed the shadow of the event horizon. We've found thousands of exoplanets. Worlds orbiting other stars, some rocky, some gaseous, some potentially habitable. We've landed robots on Mars, on asteroids, on comets. We've sent spacecraft beyond the solar system into interstellar space. All of this in just a few generations, in the lifetime of people still living. My grandmother was born before humans had reached space, before rockets, before computers. She lived to see humans walk on the moon, to see robots explore Mars. To see the Hubble Space Telescope reveal the deep universe, the pace of discovery and capability is staggering. What will your grandchildren see? What will be possible in 50 years, in 100? If history is any guide, we'll go farther than we currently imagine. We'll solve problems that seem impossible. We'll develop technologies that seem like magic. We'll push boundaries, break barriers, reach for what's beyond. Because that's what humans do. We explore, we question, we dream. And sometimes we make those dreams real. But we also face challenges: climate change, resource depletion, political instability, the risk of nuclear war, pandemics, artificial intelligence that might surpass us, biotechnology that could be weaponized. The next few centuries are critical. We need to survive, to stabilize, to mature as a civilization, to develop wisdom along with technology. If we do, the future is open, the stars are waiting. If we don't, none of this matters. We'll be another dead end, another species that never made it off its homeworld. That's why space exploration isn't just about curiosity or adventure. It's about survival, about ensuring humanity has a future, about spreading beyond one fragile planet in one star system, about becoming resilient, distributed, harder to extinguish. It's about giving our descendants options, opportunities, worlds to call home. It's about fulfilling our potential as a spacefaring species. And it's about meaning. About contributing to something larger than ourselves, larger than our brief lives. We're part of a story billions of years in the making. The universe evolved from simple hydrogen to galaxies and stars. Stars forged heavy elements in their cores and scattered them when they died. Those elements formed planets. On at least one planet, they organized into life. Life evolved, became complex, became conscious, became us. The search for extraterrestrial intelligence, known as SETI, has been ongoing since the 1960s. We listen for radio signals, optical pulses, anything that might indicate technological activity. So far, silence. The famous WOW signal, detected in 1977, remains unexplained but has never repeated. Most signals turn out to be terrestrial interference or natural astrophysical phenomena, pulsars, magnetars, quasars. The universe is noisy. But not with the kind of signal we're looking for, not with intentional communication, not with the signature of intelligence. This silence tells us something. Either intelligent life is rare, or technological civilizations are short-lived, or they don't broadcast, or we're looking in the wrong way. Each possibility has implications for our own future. If civilizations destroy themselves, we need to be careful to avoid the same fate. If they don't broadcast, maybe expansion and communication across interstellar distances is harder than we think. Maybe there are reasons, practical or philosophical, why advanced civilizations stay quiet, stay home, stay hidden. Or maybe we're the first in our galaxy at this time. Maybe intelligence is so rare, so unlikely, so dependent on specific conditions that we're alone, not in the entire universe. That seems statistically implausible given the numbers. But perhaps in our observable region, our galactic neighborhood, maybe the nearest other intelligence is in another galaxy, millions of light years away, forever separated from us by distance and cosmic expansion. This is the loneliest possibility, that we're here, aware, questioning, and nobody is out there to answer. But if we are alone, or effectively alone, then we have a responsibility to preserve life, to spread it, to fill the cosmos with consciousness and meaning. The universe is vast and mostly empty, dead, sterile. But here, on Earth, something remarkable happened. Matter became alive. Life became complex. Complexity became consciousness. Consciousness became curiosity. Curiosity became science. Science became technology. And technology might become our ticket to the stars. We are the universe becoming aware of itself. Stardust contemplating stars. Every atom in your body was forged in the heart of a dying star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all created in stellar furnaces billions of years ago. Those stars exploded as supernovae, scattering their enriched material across space. That material condensed into new stars, new planets, new possibilities. One of those possibilities was you. You are made of the cosmos, connected to everything. Every particle in your body has a history stretching back to the Big Bang. 13.8 billion years of cosmic evolution led to this moment. To you reading these words, thinking these thoughts, wondering about your place in the universe, that's not mysticism, that's physics, chemistry, biology, the story of how we came to be. And now we stand at a threshold. We can stay on Earth, live our lives, watch the stars from a distance, or we can reach out, take the risk, make the effort, go to those stars, touch those worlds, spread life beyond its birthplace. This is the choice facing our generation and the generations to come. Not whether we can, but whether we will. The technical challenges are enormous but not insurmountable. Propulsion, life support, radiation shielding, navigation, communication, resource extraction, manufacturing, governance, psychology. Each problem has potential solutions. Each solution requires research, development, testing, investment, time. But we've solved hard problems before. We learned to fly despite gravity. We split the atom despite its incredible density. We decoded DNA despite its complexity. We landed on the moon despite the distance. We can do hard things when we decide they matter. The economic challenges are significant but not permanent. Space launches are becoming cheaper. Reusable rockets reduce costs. Private companies compete and innovate. What once required superpower budgets now costs less. And the trend continues. Every year, access to space becomes more affordable, more routine, more accessible. There will be a tipping point. When space industry becomes profitable, when mining asteroids makes economic sense, when tourism and manufacturing create self-sustaining markets, when leaving Earth is not just for astronauts but for ordinary people. That tipping point might be decades away, or it might be closer than we think. The psychological challenges are perhaps the hardest. Space is dangerous, unforgiving. Mistakes are fatal. There's no 911 to call, no rescue if things go wrong. early explorers will take enormous risks. Some will die, this is certain, just as early ocean explorers died. Early aviators died. Early mountain climbers died. Exploration has always been dangerous, but humans have always explored anyway, because the drive to see what's beyond the horizon is fundamental to who we are. Curiosity is part of our nature. And there's something else, something deeper, a sense that we're meant for more than this one small world, that our potential extends beyond the cradle. Konstantin Tsiolkovsky, a Russian rocket pioneer, wrote in the early 20th century that Earth is the cradle of humanity, but one cannot live in a cradle forever. He was right. Not because Earth isn't wonderful, it is. It's beautiful, precious, the only home we've ever known. But because growth requires moving beyond comfortable boundaries, because stagnation is death, because the universe is vast and we are small and brief, and the only way to matter is to make ourselves matter, to create meaning through action. So how far can humans travel through space? Physically, within our galaxy and local group, given enough time, millions of light years, thousands of star systems, perhaps more if we adapt, if we enhance ourselves, if we merge with our technology, if we become something more than we are now. Within the observable universe, we're limited by cosmic expansion, but that still leaves billions of galaxies in principle accessible. In practice, the timescales make it unlikely we'd ever reach them as a continuous civilization. But who knows, who can predict what's possible over millions or billions of years? The real limit isn't physics, it's will, it's choice. It's whether we decide that space exploration matters, that becoming a spacefaring species is worth the cost and risk and effort, that the future of humanity includes the stars. Right now, that's uncertain. We could choose to focus inward. To solve Earth's problems first, or exclusively, that's valid, there are arguments for it. Poverty, disease, climate change, inequality, war. Earth has problems, serious ones, and space exploration is expensive. But these aren't mutually exclusive. We can work on both. The technologies developed for space often benefit Earth. Satellite communications, GPS, weather monitoring, materials, science, medicine, water purification, solar power, the list goes on. And the perspective gained from seeing Earth from space, that fragile blue marble floating in the blackness, has inspired environmental movements and peace efforts. The overview effect, astronauts call it. The cognitive shift from seeing Earth not as nations and borders, but as one interconnected whole. Now let's consider the truly distant future. Billions of years from now, the Sun will eventually exhaust its hydrogen fuel. In about 5 billion years, it will expand into a red giant. Its outer layers will engulf Mercury, Venus, possibly Earth. The habitable zone will shift outward. Mars might become temporarily habitable, the moons of Jupiter and Saturn. But this phase won't last. Eventually, the Sun will shed its outer layers, become a white dwarf, a dense, cooling ember. The solar system will be dark, cold, dead. If humanity still exists, then we'll need to have left, found other stars, other homes. This gives us a deadline of sorts. 5 billion years sounds like forever. And it is by human standards, but it's finite. The clock is ticking. Eventually, staying home stops being an option. We move or we die. This might be true for any civilization. Any species that survives long enough faces the death of its star. The survivors are the ones who learn to travel, who spread to multiple systems, who became truly spacefaring. Stars themselves have lifetimes. Small red dwarfs burn slowly. They might last trillions of years. Our Sun, a medium-sized yellow dwarf, lasts about 10 billion years total. Massive blue stars burn fast and bright, Some last only millions of years before exploding as supernovae. The universe is about 13.8 billion years old. Most stars that have ever existed are still shining, but eventually star formation will slow. The universe will use up its hydrogen. Brown dwarfs and red dwarfs will dominate. Then even they'll fade. In the far future, perhaps 10 to the 14th power years from now, 100 trillion years, the last stars will die. The universe will enter the degenerate era. No more fusion, no more starlight, just the fading remnants. White dwarfs, neutron stars, black holes, brown dwarfs cooling into black dwarfs. The universe will be dark, cold, approaching absolute zero. If any civilizations survive, they'll need to tap exotic energy sources. Hawking radiation from black holes. The rotational energy of neutron stars. They'll need to think slowly, conserve every joule, stretch their existence across unimaginable timescales. Eventually, even black holes evaporate. Hawking radiation carries away their mass. Small black holes evaporate quickly. Stellar mass black holes take 10 to the 67th power years. Supermassive black holes take 10 to the 100th power years or more. When the last black hole evaporates, the universe will contain only photons, neutrinos. Perhaps some exotic particles. Everything spreads so thin that interactions become vanishingly rare. This is heat death, maximum entropy. The universe reaches equilibrium. Nothing changes anymore. Time becomes meaningless. This is the ultimate limit. Not a limit of distance, but of time. The universe itself has a finite lifespan, at least in terms of supporting complexity, supporting life, supporting thought. We don't know if there are ways around this, perhaps new physics we don't understand. Perhaps ways to access other universes, other dimensions, or perhaps this is simply the end. Everything that begins must end, even the universe itself. But we're not there yet, we're not even close. We're in the stelliferous era, the age of stars. The universe is young, vibrant, full of energy and possibility. We have billions of years ahead of us, trillions if we're clever. That's enough time for things we can barely imagine, for evolution, for expansion, for discovery, for transformation. So when we ask how far humans can travel through space, the answer has layers. Practically, with current or near-future technology, we can reach Mars, the asteroid belt, perhaps the moons of Jupiter and Saturn within a century or two. With advanced propulsion, we can reach nearby stars, dozens or hundreds of systems within tens of light years, within thousands of years. With patient expansion, we can spread across the galaxy, millions of star systems within millions of years. With determination and luck, we might reach nearby galaxies, the local group, within tens or hundreds of millions of years. But beyond that, physics draws boundaries. The expansion of the universe creates a cosmic horizon, about 16.5 billion light-years. Beyond that is unreachable, forever inaccessible. And even within that horizon, most places are receding faster than we can approach. The window of accessibility is closing, not in human terms, but in cosmic terms. Eventually, only our local cluster will be reachable. Everything else will disappear beyond the horizon, and time itself imposes an ultimate limit, the heat death of the universe, the end of complexity, the end of everything. But that's so far in the future that it's almost meaningless. 10 to the 100th power years, a number so large it defies comprehension. By then, anything recognizable as humanity will be long gone, transformed, evolved, transcended, or extinct. What matters is what we do now. In this era, in this moment, we stand at a threshold. We've learned enough to ask these questions, to understand the cosmos, to glimpse our place in it. We have the beginnings of the technology to venture out, to take those first steps, to become something more than a single planet species, but we haven't committed, haven't decided as a civilization that this is a priority, that exploration matters, that the long-term survival and flourishing of humanity is worth investing in. We face challenges: climate change, political instability, economic inequality, pandemics. These demand attention, resources. But they don't have to be either-or. We can address problems on Earth and reach for the stars. The technology developed for space often helps on Earth. Satellite communications, weather monitoring, GPS, medical devices, water purification. The list goes on. Space exploration drives innovation, creates jobs, inspires young people to study science and engineering, reminds us that we're capable of great things, that we can work together toward ambitious goals. And there's something else, something harder to quantify but deeply important. Space exploration gives us perspective. When astronauts look back at Earth from orbit, they report a profound experience, the overview effect. Seeing our planet as a fragile blue marble, no borders visible, no nations, just one world, one humanity, shared and precious. This perspective changes people, makes them care more about protecting Earth, about cooperation, about the bigger picture. Carl Sagan spoke about this beautifully. He called Earth a pale blue dot, a mote of dust suspended in a sunbeam. Everything we've ever known, everyone we've ever loved, every human who has ever lived, all on that tiny world. It's humbling, perspective-giving, and it should make us kinder, more thoughtful, more aware of how rare and special our existence is. Now let's consider the truly deep future. What happens to space travel in a universe that continues to expand and age? In about 4 billion years, the Andromeda Galaxy will collide with the Milky Way. This sounds catastrophic, but galaxies are mostly empty space. Stars are so far apart that direct collisions are unlikely, but gravitational interactions will reshape both galaxies. They'll merge over hundreds of millions of years, form a new elliptical galaxy, sometimes called Milkomeda. The Sun and Earth, if they still exist, will be flung into a different orbit, perhaps closer to the galactic core, perhaps farther out. The night sky will transform, unrecognizable. Long before that merger, the Sun itself will change. Stars are not eternal. They're born from collapsing clouds of gas and dust. They fuse hydrogen into helium in their cores. This releases energy, creates pressure that balances gravity. For billions of years, equilibrium holds, but eventually the hydrogen runs out. For stars like the Sun, this happens after about 10 billion years. The Sun is currently about 4.6 billion years old. It's middle-aged. In another 5 billion years or so, it will exhaust its core hydrogen. When that happens, the core will contract and heat up. A shell of hydrogen around the core will begin fusing. The energy output will increase. The outer layers will expand dramatically. The Sun will become a red giant. Its surface might reach Earth's current orbit or beyond. Mercury and Venus will be consumed. Earth's fate is uncertain. The Sun will lose mass as it expands. Earth's orbit will shift outward. It might survive, but even if the planet itself isn't engulfed, the heat will boil away the oceans, strip away the atmosphere, sterilize the surface. Earth will become uninhabitable long before the Sun dies. This gives humanity a deadline, not in our lifetimes, not in the next 1,000 or million years, but in a few billion years we must leave Earth or perish. The planet that gave birth to us will become our tomb unless we move. This is the ultimate motivation for becoming a spacefaring species, not just curiosity or resources or backup, but survival. The universe doesn't care about us. It follows its laws indifferently. If we want to continue, we must adapt, must leave, must find new homes, and we can. 5 billion years is an eternity by human standards. Longer than Earth has existed as a planet, longer than life has existed on Earth. If we use even a tiny fraction of that time wisely, we can spread to countless worlds. When the sun becomes a red giant, humanity could be scattered across the galaxy, living on planets around younger stars, on artificial habitats, in forms we can't yet imagine. The death of our home star would be a historical footnote, a distant memory. Not an existential threat, but the universe itself is also mortal. Eventually all stars will die. Star formation requires gas and dust, clouds of hydrogen collapsing under gravity. But with each generation of stars, more hydrogen is fused into helium and heavier elements. More material is locked up in stellar remnants, white dwarfs, neutron stars, black holes, brown dwarfs that never quite ignited, planets. The raw material for new stars depletes. Star formation has already declined from its peak billions of years ago. It will continue to decline. In about 100 trillion years, the last stars will burn out. The universe will enter the degenerate era. No more fusion, no more starlight, just the cooling remnants. White dwarfs gradually fading to black dwarfs, neutron stars spinning down, black holes accreting what little matter remains. The cosmos will be dark, cold, nearly empty. Any civilizations that survive will need to huddle around the last energy sources, white dwarfs, black holes. They'll need to be incredibly efficient, conserving every erg of energy, perhaps slowing down their thought processes to match the available power, experiencing subjective eons while objective time crawls forward. Even black holes don't last forever. Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon. This is Hawking radiation. It's incredibly faint for large black holes. The supermassive black hole at our galaxy's center will take about 10 to the 100 years to evaporate. That's a 1 followed by 100 zeros, a number so large it defies comprehension. The universe is currently about 10 to the 10 years old, 13.8 billion years. A black hole evaporation takes 10 to the 90 more years. Time spans compared to which the current age of the universe is instantaneous. But eventually even the black holes will evaporate. The universe will reach maximum entropy, a state called heat death. No more energy gradients, no more structure, no more change. Just a thin, cold soup of fundamental particles and radiation spreading forever through an endlessly expanding space. This is the ultimate fate according to our current understanding of cosmology. Not a bang, but a whimper. The slow, cold, dark end of everything. In such a universe, complex structures like life cannot exist. There's no energy to drive metabolism or thought, no stars to warm planets, no planets to live on. The laws of thermodynamics are absolute. They cannot be cheated. Entropy always increases. Order gives way to disorder, complexity to simplicity, life to death. Heat death is final, irreversible, the end. This vision troubled many scientists and philosophers when it was first realized in the 19th century. If the universe must die, if all structure is temporary, if entropy wins in the end, then what's the point? What does anything matter against the backdrop of cosmic futility? These are not easy questions. Different people find different answers. Some embrace the temporary nature of existence, find meaning in the journey rather than the destination. Others hope we've missed something, some loophole, some escape. Could advanced civilizations escape heat death, perhaps by manipulating the laws of physics themselves, creating new universes and migrating to them. This is pure speculation. We have no idea if it's even theoretically possible. Our understanding of physics is incomplete. We don't know what dark matter is. We don't know what dark energy is. We don't understand quantum gravity. There might be deeper laws, underlying structures we haven't discovered, or there might not. The universe might be exactly as cruel as thermodynamics suggests, but again, this is trillions upon trillions of years in the future. Timescales so vast that trying to imagine them breaks the mind. In the near term, the universe is young, full of stars, full of energy, full of possibilities. Humanity has time. So much time. If we use it well, we can explore, create, build, experience wonders we can barely imagine. We can fill the cosmos with consciousness and meaning and beauty. Not forever. Nothing is forever, but for a very long time, and maybe that's enough. Maybe the fact that it ends makes it more precious, more meaningful. Every moment is unique. Every experience unrepeatable. Every life valuable precisely because it's finite. We are the universe become aware of itself, stardust contemplating stars. Atoms arranged in such a way that they can wonder about atoms. For a brief cosmic instant, complexity and consciousness emerge from the chaos, and that's extraordinary. If you made this far, make sure to subscribe to the channel and give a like. And have you ever wondered how long it would really take to reach Mars? Discover why you can't simply point a rocket at Mars and go, how the 26-month launch window cycle imprisons all mission planning, and why the total round-trip duration stretches to longer than you can imagine. See you there.